The first example from this module on the dynamics of circular motion is about the roller coaster that is actually completing a loop-the-loop motion, and it's at the top of a circular track. The question is, what must be the minimum speed of a roller coaster when upside down at the top of a circular track if the passengers were not to fall out? The radius of the curvature of the track is 15 meters. Here's the track. Here's the radius of curvature, 15 meters. And here's one car of the roller coaster. Remember, notice it's on the bottom side of the track. I'll choose for the positive direction to be up. And with that, I'll draw the vectors for the forces. First is gravity, of course, downwards towards the center of the Earth with components 0 and minus mg. Next, because the roller coaster is completing actually a portion of a circular motion here, I know its velocity is going to be in the horizontal direction just for one instant there as it's passing the top of the track, and it's going to have a centripetal acceleration pointing towards the center of the circle. So for when the roller coaster is exactly at the top, the direction towards the center of the circle is down. And that's why I drew the vector for my acceleration downwards. This is not the g acceleration associated with free fall. This is a centripetal acceleration. Its magnitude must be equal to v squared over r. In components, that will look like 0 for x component and minus v squared over r. Those components actually change for every point along the track, so I want to emphasize that this is only for when the roller coaster is at the very top of the track. The trickiest point, arguably, here about this problem is the normal force. Many students make the mistake to draw the normal force upward, but if you were to point that vector upward, it would mean that the track actually can hold on to the roller coaster. And pull it upwards. That doesn't make sense, especially since the roller coaster is moving along the bottom side of the track. The only option here is to push away from that contact. That's what the normal force always does, and because of that we have to draw the vector downwards. So the components for the normal force vector here will be 0 and what I have marked as minus Fn. Let me apply Newton's second law now for that car. Of course, I'll write down the equation for the y components. I have no other components anyway, and that will be minus mg, the gravitational component. To that, I will add the normal force component, minus Fn, and that has to be equal to m times minus v squared over r. That's the y component of the acceleration. All three terms here show up negative, and sometimes I get this question from students who are somewhat experienced with physics, asking me if they could use a different direction, if they can actually flip the direction for the y so that all the vectors are aligned with the positive y, and then we can actually write the equation plus mg plus Fn has to be equal to m times plus v squared over r. By all means, this is a perfectly valid way to go about writing the equation. In fact, if I were doing it for myself, that's probably how I would have written the equation. I am reluctant to do that when I show problems to students who are relatively inexperienced solving physics problems, because I know it could get somewhat confusing if we keep changing the directions of the axis. So that's why I have chosen to stick with our standard choice up. But it doesn't matter, we can always go back to our equation here with the minuses, with the negative terms, and just apply algebraic rules. I can multiply every single term here by -1, or in other words, I can cancel the minuses, so I can get mg plus Fn is equal to mv squared over r. So that's identical to the equation that I would have gotten with the opposite direction of y-axis. So anyway, the normal force here appears to be equal to mv squared over r minus mg. And here is a good moment to pause and think about it. What is it that will ensure that the passengers were not to fall out, that they will remain in their seats? What quantity here from our mathematical equations is the one connected to the passengers not falling out? When we think about the passengers remaining in contact with the seat, we immediately can recognize that that is actually the normal force, because the normal force stands for the interaction between the interaction that happens at the contact between two objects. So if we want to ensure that the passengers remain in contact with their seat, all we need to do is require that the normal force remains in our equations. So in other words, it has to be positive or at minimum equal to 0, but it should never, my equation should never give me a negative normal force. From previous examples, we have seen that when the normal force shows up negative, that means that things are not physical, they don't make sense, and we actually don't have a normal force. We have lost that contact. So here it is. We're going to require that mv squared over r minus mg, which was equal to the normal force, is greater or at minimum equal to 0. When I move the mg term to the right hand side here of the inequality, I see that the mass actually cancels out, which is very fortunate because the problem didn't give us the mass of the roller coaster. Many problems won't give you the mass because this is very common for the mass to cancel. So I can see that v squared over r has to be greater or equal to g, or v squared itself has to be greater or equal to gr. I can focus on the minimum speed here. That is the minimum speed for the roller coaster so that the passengers don't fall out, and that minimum speed will be equal to square root of gr. What is left now here is just to substitute 9.8 for g and 15 meters for r and find out that the minimum speed that the roller coaster must maintain is 12.1 meters per second so that the passengers do not fall out.